So again, I'm Josh Tenenbaum. I'm going to just introduce our panelists and then say a few stage-setting remarks and then open up our discussion. So over here on the left, we have David Siegel. Thank you, David, for everything, including joining us for this discussion. Here we have Nick Roy, he's one of the Quest leaders, was our original director of engineering and part of the strategic leadership team, and also is a core member of the Embodied Intelligence mission. And Nick's specialty is robotics, but he really works on the full range of cognition in AI systems and also human-AI interaction. Then we have Fedorenko, who you've heard of, well, definitely heard of and heard from. She definitely needs no introduction. And Rebecca Saxe, who I know many of you know. She's been a member of the Developing Intelligence mission and participant in some of the language projects as well, basically some of all the projects you've seen here. And she has been working on some preliminary steps towards a new social intelligence mission, which Jim talked about. It's just exploratory at this stage, but I hope she might say a little bit about some of the things that we're thinking about there, she's thinking about, and both on the research side as well as in the area of impact. Okay. So what are we doing in this panel? This is the forward-looking part. You've heard from our really awesome mission teams. You've heard about our North Stars. Think of these North Stars, again, as their aspirational goals. Like a North Star, as a guide to navigation, it's not a thing you actually get to. It stays fixed, but you head towards it. It gives you clarity on what you're aiming towards. It helps you plan your next steps and your long-term roadmap. Okay. So thinking about these North Stars, the questions here, as we go into the next stage of the quest, how should we be approaching this kind of vision? What should our next steps be? What should our long-term roadmap be? This is a great opportunity to take stock. Okay. What else should we be doing? Are there other missions that are essential to the quest that should be in this picture on our roadmap? For example, social intelligence. If we succeed, if we even make small steps towards these goals, what will the impact be? And what is the relation between impact and the drive that a number of us has, like Jim said at the beginning, but I think everybody here feels the urge to have our basic research have impact. What is the relation between the impact goals that we might want for society and the basic research we do here in the university? So just again to set the stage, as David has said, I think the most succinctly of all of us, the quest is about understanding the brain in the era of AI. That's what it's about, okay? And this is a unique era. Highlighting things that we all know about the current era from the news. Literally, I restricted myself to news headlines from the last 2 days, but you can see how AI is everywhere, which includes the massive economic impact it's having, as well as the potential fragility for the economy, with everything being driven by AI and the interlocking investments of the various big tech players there, but also the ways in which AI is potentially responsible for and sometimes might be a tool for addressing various kinds of mental health crises, whether it's delusional chatbot spirals or teen self-harm or worse. There's a lot going on in our minds and in our minds with AI these days. This extends to how the broader world is thinking about the relation between the AI systems that industry is building and the way our own minds work. So going back more than the last 2 days, but a couple of weeks, for example, we see in the New Yorker or the New York Times articles like this. People taking seriously at the legitimate proposal that maybe what goes on inside an LLM is a model of what goes on inside our own minds. Or the AI systems may not be only intelligent, they may be conscious. This is by a philosopher of mind. That New Yorker article features a number of our Quest colleagues, including Ev, and a number of alums here. And you can see just on the MIT Daily Update today, I saw this great new recent MIT news story coming out of Ev's lab, again, which I think maybe she might talk about. I will encourage her to talk about some of this latest work from her lab, really trying to establish a correspondence between some things that goes on in reasoning-trained language models and maybe some aspects of human reasoning. Okay, so how do we think about this? I'm just going to leave you with just sort of some motivational pictures, I guess. But I think the way a number of us see it is that right now, there's all this stuff happening in AI systems being developed in industry. And then there's a number of us over in cognitive science and cognitive AI, as well as computational neuroscience, who are really interested in building engineering-style models of the brain and the mind. That's fundamentally, the quest is sort of between these things. Fundamentally, the quest is about NI, natural intelligence, and models and how those gain from and contribute to AI systems. But how should we think about these things? Well, really, we can think of, one way to think is that the activities going on in industry and the activity going on inside the quest are like two paths or routes up the same mountain, where the mountaintop is an understanding of the brain as in a machine executable model. Okay, that's the brain and all the aspects of intelligence that it gives rise to, that is the peak. And we have two different routes to get there. We might make progress starting from a computational model of natural intelligence, and the steps of progress there might not look like much progress on the industry side at the early stages. Likewise, some of the earliest steps on the industry side might not look like they really have much to do with the natural intelligence side. But as these routes start to move up the mountaintop, there are ways they can interact. AI systems can be tested as models of natural intelligence and can contribute there. Some of us, especially some people on the panel, and some of us, that's been their focus. It's also the case that NI models can start to actually come back and help to drive forward what's going on in industry-led AI systems. And those together can bootstrap each other. And the more progress you make, the more potential for bootstrapping there is. So, I'd like the panel to consider what are the different routes for interactions between these that you might see in this picture, as well as how even at early stages there can be impact from either of these routes, and again increasing kinds of impact outside of the basic research, and how the mountain that we're climbing really isn't just the only mountain. I'm sure, as we've seen many times, that as we make progress towards what we think are our North Stars, more peaks, more mountains beyond mountains will reveal themselves, and we want to understand and plan for what that longer-term roadmap would look like. So that's it for the pictures. And with that, I will turn it over to our panelists. So I thought we would start with David to give his perspective on how to think about the relation between what's going on in AI in the broader world and what the Quest is doing.
Well, your introduction was quite good. The way I look at industry today is, initially there was, in a way, more pure research focus. But as the chatbots caught everyone's attention and attracted vast amounts of funding, and it began to appear to be a very, very large product, the focus has somewhat shifted to just trying to find ways to get revenue to pay for the scale-up that they believe will continue to improve the performance. And so you have some kind of weird effect going on right now where, to some extent, they probably can't really take so many chances because they have to really project that they understand how this is going to work. Because how do you raise trillions of dollars if you're going to basically say, we're not sure if any of this is going to work? And I think it's all honest. I think that they believe that it's going to scale up and that the intelligence will continue to grow, but it might not. And this is beginning to get some amount of attention. And so, what you really see, and you took it down, but the term AI is a very broad term. I think I was speaking earlier today about how it's a vague term. Mostly what the money appears to be going into is LLMs and a particular architecture for LLMs, one that has no one needs to describe what it can do because everyone uses it and you can see what it's good at, what it's not good at. But to me, I'm a little confused because not exactly sure what sort of the objective function is. So in fact, the industry doesn't even really know because benchmarking is like, how do you know if you're making it better? Better in what dimension? Are you really, I don't believe that chatbots are being made for a well-defined reason. They just kind of want to drive revenue, I think. So the real metric is how much money can they get for people to use it, which is not the same as, are we on the path to ever greater intelligence? And if you ask someone, by the way, what's the definition, Josh, what's the definition of intelligence? No one can really define it. And probably there isn't even one definition. It probably, there's social intelligence, there's mathematical intelligence. So I think it gotten mushed up. And that's not to say that industry AI isn't going to create a vast new industry, and maybe enough money will be made with products that people want to use to finance the expansion. That's possible, but they're not really focused on the same problem that we heard today people are focused on. It's just a different problem. So I'm not being critical of industry, but I think people have to recognize that they're not really working on what people here are working on.
Yeah, okay, well, thanks, David. That's a good way to put, I think, a lot of the basic issues at stake. And again, I don't know if, you raise another, I think, an even deeper, bigger point. Let me just, I don't know if I'm getting interference from that, but, which is what is intelligence anyway? Like, you certainly hear this a lot in industry or in the broader world. Nobody really knows how to define it. But in some sense, as you saw, whether it was in Ev's talk or all the talks here, it's not like we, in the Quest, say, here's the simple, crisp definition of intelligence. But there actually are some, I'd say, shared commitments that are really deeply grounded in science, that are grounded in our basic understanding of what minds and brains do, and that informs the kind of computational models that we're building. Whether it's the ways we're trying to draw on and adapt from AI tools developed in industry, or develop new kinds of models that, again, are not really the ones that industry is focusing on because they don't clearly drive revenue, but they might drive what we think of as human intelligence. So, again, I'd like to invite all the panelists to.
Why don't we start at that next?
Yeah, sure. Well,
I can go.
I was hoping we could go this way because I was just thinking. It sort of mirrors like some of the missions we have, and Rebecca might talk about some of the new missions. But I think each of you guys, give me your take on either what you think of are ways that the Quest should be drawing on industry ideas that it isn't yet, or key things that we need to be doing more of that industry isn't doing.
Sure.
Yeah.
So you said it very nicely, Josh, is that I'm a roboticist, and that's sort of how I think of myself. And first of all, robotics is incredibly punishing. I warn people away from being roboticists because there's so many things can break. But one of the things that we have to struggle with is the reality of the physics of power and computation and embodied intelligence. I'm part of a couple of Army programs, and we were going to do a field demonstration a couple of years ago, and we added up how many actual NVIDIA class full-blown desktop GPUs would be required to run the entire quote-unquote intelligence system. It was 17 sort of NVIDIA desktop computers on a robot this size. And so one of the things that I'm excited about is the Quest, compared to industry, the Quest has the disadvantage, in some sense, of not having to focus on a necessary product, but it has the advantage of not having a huge amount of money, just as like VC scale money. We're very lucky to have a large amount of money, but VC scale money thrust at them. And so that forces us to actually take seriously a lot of the constraints that inform a lot of intelligence. I think something that's very poorly understood, and I spend some of my time at a self-driving car company, so I get to see what it takes to actually deploy a self-driving car company. And it's very poorly understood how much human labor goes into actually supporting the operation of these vehicles on a tick-by-tick basis, as well as all of the back-end operations required to support the intelligence. I don't mean cleaning the cars and all of that. What I mean is actually managing the data and overseeing it and curating it, and actually dealing with the sensor data that happens. And we know there are some circumstances that our car can't operate, and we have to backfill with human intelligence a lot of the time. And that is a huge cost that the Quest can't undertake and shouldn't undertake. And so that forces us to, I think, like explore that mountain that you're describing. Flip that around though, and I will say that there's enormous value in actually being forced to focus on self-driving cars. So it focuses the minds of that company very carefully. And I think you asked one of the questions, Josh, is like, what should the next phase of the Quest look like? And I think that like, Leslie and I, in conversation over the last few weeks, have come to realize like we do need to like focus on our tasks a little bit more, embodied intelligence, and pick tasks that do mirror what humans can do in terms of embodied intelligence. Roboticists are very good at picking tasks. They're very good at picking tasks that kind of align with what the robot can already do. They're not so good at picking tasks necessarily that like elicit something about natural intelligence. So I think we should hold ourselves to a little bit tighter account for the tasks that we're picking and evaluating, and actually like focus on those as quote unquote our product, even though not selling anything, but I think that would be where I would go as I think. So it's sort of funny to think about industry has the advantage of having to build a product, but the disadvantage of having like, all of these resources that a lot of them cut corners because they have to, and so we can't cut those corners.
Yeah, no, it's putting the cost thesis out there is interesting. I think, I said this, Leslie will often say that, what we're doing in the Quest is trying to do for our robots what intelligence or what evolution did for us, right? Evolution over vast amounts of time, much longer than our lifetimes, built a cognitive architecture in the brain that really makes us intelligent from the beginning. And we can think about, or maybe learn from science, like the new working group Nancy and Leslie are setting up, is like learn from brain architecture and cognitive architecture how to do that. In contrast to, like, if you have all the money in the world, maybe, people in industry will often say, oh, we're just redoing evolution, right? Like, yeah, it learns from vastly more data than a child, but that's okay, because this is meant to be like evolutionary scale learning, not learning in the span of a lifetime. Those are very different. But as David says, right, it's hard to know how much it's going to cost, right? Actual evolution, the actual process of evolution, took a planet-sized computer. It took all the resources of a planet over billions of years. And if you like extrapolating power law scaling curves, it is plausible. That, like, you can't, who knows how it's hard to bet on. It's possible that it might, we might take all the resources of the planet for that scaling route to achieve to get to the top of the mountain it's aiming for. And, I don't know that we can afford that. So, good point to draw that contrast. And I think also, the reason why we're working with the roboticists that we are, for those of us coming from cognitive neuroscience, is because we do see a synergy between the basic problems of like what brains do, even brains of young toddlers, like the ones who are still saying or shoes or bear, is like how we understand the world in front of us, how we move through it, how we navigate, how we pick up things and build things. So I think actually more and more the cognitive and developmental side of the Quest combined with where the embodied intelligence and robotics are moving, like actually the task, the space of problems is also converging. So that's exciting. Ev?
Yeah, well, so there's a couple of things to say. I mean, one is I just think it's an incredibly exciting time to live in. I grew up, like my whole academic training has revolved around this point that the human brain is the only thing that can do language. Well, that's clearly not right. We have these things that do language and they do it really well. So suddenly this whole premise is just out the window, and I've spent years being jealous of my vision colleagues who have mice and macaques who they can do things with that I wish I could do with humans but can't for good reasons. And suddenly we have these implemented models that we can take apart in whatever way we want. I want to train them exactly knowing what goes in as the data, what the algorithms are, and then examine how they do on various downstream tasks. And it just still blows my mind that there's language researchers out there who just kind of poo-poo these models and say things like, well, they don't learn language like children, therefore, forget it. And I'm like, we have a thing that does this behavior that we've been studying for many years, and now we can do so much more. It's an incredible tool. Sure, they don't learn language like kids, but make them learn language like kids more. Build in biological constraints, build in cognitive constraints, put in some, whatever you want to call core knowledge, some very early learned representations about the world and about social agents, and see if learning language on top of that will lead to more language-like, more human-like developmental trajectories. So I just think it's an incredibly exciting time to be around, to be alive and be doing this work. Besides, like Josh alluded to, so when these first kind of generation of language models came about, they were extremely limited in reasoning. And in fact, it was really surprising to me how much people were anthropomorphizing these models and thinking that they're conscious and they want to marry them or whatever.
This is like the GPT-3
Yeah,
era.
that level,
Yeah.
exactly. Whereas, like, you know, you ask them simple math and maybe occasionally they get it right, but you modulate the prompt a little bit and they fail, and it's like, okay, well, that's clearly not a thinking brain behind it generating the stuff. But it was a very unusual experience, right? Phenomenologically, we're not used to having something have a conversation with us that doesn't have anything that has an intent to communicate a meaning, right? That's just an unusual, so maybe that makes sense. But then these later generations of models, including models that have been imbued with some additional capacities, like fine-tuned on reasoning problems with feedback on which solutions are correct, they're making incredible strides and actually achieving very surprise on tasks that I wouldn't have predicted they would do so well at.
You mean like math problem solving?
Math
or
problem solving,
logic,
for example. Yeah,
some of
math
those
and
things.
logic. And so the
Coding.
work that Josh mentions, Andrea DeVardo, who led this work, showing that for now, just looking at how long it takes models to think. So some of you may know these latest generation of models, which are encouraged to do chain of thought reasoning, right? Thinking step by step, which is kind of the core kind of premise of human intelligence, where we break things down into steps to solve a complex thing. And it turns out that across quite a few different types of reasoning tasks, models take longer to generate longer chains of thought, similar to how humans take longer to respond with an answer. Okay, so there's something about the computational cost that seems to be similar between models and humans, and now there's a lot more to do to understand whether the actual kinds of processing that happens in these two systems is similar, in which ways it's different. But again, we can take these AI models from industry, but we can also compare them to human brains in ways that, again, just asking questions that we couldn't ask before, like, is there more than one way to build intelligence? Like, can you really get to that same point on the mountain from two very different ways? We just couldn't even conceive of how to ask these questions. The only model of general intelligence we've had is the human brain, and it has a particular thing, particular structure, modular structure, but maybe those are all kind of accidents of evolution, right? Maybe it is actually possible to build intelligence in a fundamentally different way, and maybe some consequences are different, but we can ask these questions. And I think that's really exciting.
Cool. So can I just dig into that a little bit?
Go for it.
Right. So this is the work that I was alluding to that you can read about it at MIT News right now. Really cool stuff. And I think it illustrates like one version of this picture, right? Where, and partly what I want to ask you a little bit about is the potential tension between that and what you talked about in your talk, right? So on the one hand, in work you've been doing for a while, you emphasize that language and thought are different, and the human brain has, 1.5% of its volume does language, and then there's all these other things that, like logic and problem solving and math and chess, and if you have a stroke and you have aphasia, you can still do all those things. And I've seen some of that. I've even collaborated a little on that. It's really amazing that it's true. At the same time, you're saying, okay, like in the work with Andrea, you said, okay, well, we can take these reasoning trained models and that basically the number of tokens that they produce in their chain of thought between when you ask them a question and the answer seems to correlate with the reaction time or the amount of processing that humans do, at least in some kind of reasoning tasks. Right, but is that reasoning or not? I mean, because what it is producing an internal, inner dialogue or inner speech. So, you could think of that as like, okay, here's this model from AI, and now you're bringing it around to the other side of the mountain. But how do you think about the interplay between those sets of ideas and tools in your work or more generally?
That's a good question. So although these reasoning models generate these chains of thought, there is accumulating evidence that the actual code of computation is not natural language. And in fact, oftentimes the content of the traces that they generate has very little to do with the stuff that's going on. So I don't know, you can think of it as like buying time, right? Like sometimes somebody asks you a question and you're like, after thinking you do a bunch of filtering and you're doing this computation very intensely. Right. And then you can produce the answer by yourself sometime. And it's not like we fully understand how exactly these models do the computation, but I would bet money
so like the
that
words
it's
you
not.
see are just like they're just like some projection. It's just like some people when they they think they
That's
say a
right.
lot of words, and other
I
people are just
hear. That's
right.
right.
Yeah, no, that's
right.
great. That
That's
really
right.
makes a lot of sense, and I think
Yep.
you're right. That's really interesting, and it would be really interesting to dig into that more in both analyzing the models and seeing if that can explain what goes on in humans, including some of the
That's right.
individual variation.
Exactly.
Can I also ask you about the other thing you said, or maybe just, I think it's definitely an area that, like this was this question about like learning like a child. This is something that you guys alluded to with Jacob. We in the development mission are really interested in this. You know, as you say, I think it's not fair to dismiss a large language model as a model of human language simply because it learns in a very different way from a lot more data than a person, right? I think that's clear. At the same time, it is like it's become very clear, I think, to many people in cognitive science and in machine learning that there's this grand challenge, this really big question. Okay, but how do human children learn language? Because we get, you know, the estimates are roughly like maybe 5 million words a year, roughly. So between 10 to 100 million words are considered like the span from the first couple of years up to young adulthood. And it's this open challenge. In fact, there's a challenge competition called the Baby LM Challenge. I'm sure some of you have heard of it. Organized by a number of people, including Cheng Xu, one of the Quest postdocs, and others who came out of MIT, and many people beyond MIT. And that challenge is really interesting. So it's been running for I think that it's in its third year now. And what we see from that, right, is that it turns out that training a what you might call a small language model, like a GPT-2 size transformer, which are actually the models that Ev's group and a Quest team from Jim's lab and Nancy and me a little bit showed a couple of years ago. Those GPT-2 scale models are actually pretty good models of the language network. But those models trained on just 100 million words are coming pretty close to human level performance on syntax. So just on like language processing at the sentence level, the kind of thing that the language network does. But what was really pretty cool that was shown just in last year's Baby LM Challenge is the organizers used the EWalk data set, which was the Quest data set that Jacob talked about at the end of his presentation. So that test of common sense knowledge, physical, spatial, social, emotional, mental state reasoning that Anya Ivanova and others from the Quest put out there and showed that actually language models were still, you know, not at human level performance in all these kind of very basic common sense reasoning tasks. The Baby LM folks used that as a hidden help. They didn't tell they told the people they were just trying to get syntax for 100 million words, but then they said, well, we're also going to evaluate you on the EWalk. And it turned out they were basically a chance. So it really showed very dramatically that from 100 million words, you can learn, you know, the grammar at the sentence level, but you can't learn to think even in basic common sense ways. So it highlights the challenge. But I think, as you were saying, and I think this is, you know, I don't want to commit my colleagues to this, but I think a number of us are excited to try to do this over the next stage, is to really take a cognitive approach to that Baby LM challenge seriously and to say, okay, could we build something that combines statistical sequence learning from, let's say, 100 million words with what we think is the computational cognitive architecture that might be built in, and somehow put those together to actually get something which can learn, like a child does, from just tens of millions of words, to understand language, but also to think in these common sense ways, or at least to be able to answer questions like a young child, and then maybe see what kind of bootstrapping loop comes from that. So are we doing it?
Yeah.
Yeah, okay, we are. Yeah, we're doing it. All right. Again, I think many people in the world are working on this.
Where do I sign?
You already did. No, but a number of us are excited about this. And you know, again, I think a lot of people in the world are working on this, but the combination of ideas and tools across the Quest teams, I think, really position us well to make progress on that. So,
I know, that's right.
How about you, Rebecca? Your take on our moment.
Well, I'll give a pitch for why part of the future of the Quest is social intelligence, although I'll start by saying that expression can be taken to mean almost anything, so it's a little bit dangerous. But starting from, David, where you pointed us, which is the enormous and almost unexpected success of chatbots, right? That chatbots are in use at a dramatic scale right now. And one of their most frequent most substantial uses is to form relationships, right? What people are doing with chatbots is forming relationships with them. And in fact, apparently the most frequent use of chatbots is young men having girlfriends. So if you think about what does that tell us about chatbots, I don't know, but it tells us a lot about us, right? What our needs and motivations are. Given a tool that could do anything, what we do is form relationships with them. And so social motivation, the desperate need to form and understand human relationships, has all the properties of intelligence that we've heard about so far today. So it's among the first emerging capacities of human infants. It's actually the only thing a human infant needs to do to survive is to form social relationships, partly because human infants can't do anything else. They can't navigate, they can't speak, they can't forage, they can't generate their own food. The only thing they can do is form relationships with other humans who will keep them alive. Social intelligence, interestingly, occupies a huge amount of human cortex. So by contrast to language, which has relatively little of the human cortex, one of the biggest early surprises of functional neuroimaging when it became possible and gave us our first looks at human brains as opposed to all the non-human brains that have been studied up until that point, is that by comparison to non-human brains, human brains contain huge swaths of cortex dedicated to one or another aspect of social life and social cognition, including everything from social perception, the quick ability to understand who you're looking at and what they're expressing to you, which is more like the kind of perceptual intelligence that Jim talked about, all the way to problems that involve reasoning at timescales you never deal with in vision, like what people will do over decades when they work together in a quest like this. So it has a huge scale of problems. They are covered by dedicated areas of cortex. They're also often sensitive measures of failures in mental health. So mental health leads to failures of social relationships and also is often sensitively detected by failures of social relationships. Many neurodegenerative and neurodevelopmental disorders come to medical attention not from the person seeking care, but from their family or social relationships coming to seek care. So it has all of these different components. And also, it feels to me right now that the modeling capacity that we have in our contemporary computational models is just reaching a point where we can make real progress on this. So I'll just say as a little bit of biography, I started working on human social cognition and the brain systems that support it 25 years ago. I worked on those brain regions pretty intensively for about 15 years. And about 10 years ago, I stopped. I stopped working on human social cognitive neuroscience because our models couldn't generate hypotheses worth testing. So in the way that Jim said, to do the right experiments, you need the right models. And I got to a point where I could keep doing the experiments, but I knew I didn't have the models. And so I stopped. I asked a grad student to work on a project I thought would be a 1-year project that has turned out to be a 10-year project to develop the first computational models that could do some of what human cognition lets us do in the social realm. And I think that those models are just now beginning to bear fruit. So Josh briefly mentioned Memo, Kartik Chandra's domain-specific probabilistic programming language, specifically for reasoning about other minds. This language has other properties that we've talked about today, in that it lets you very efficiently and in a data-efficient and cost-efficient way do reasoning problems that would be extremely expensive if you tried to do them in a domain general model. And I know this because in my own lab, we had built those models before Kartik and Memo existed. And when Memo existed, models that would take us 3 days to run suddenly took us 3 minutes to run. And that difference, it not only makes the grad students happier, though it really does, but it just changes the scope of our ambition, right? If it takes you 3 days to run one model, you could imagine running 10, but you wouldn't try to run 10,000. You just wouldn't. And so the complexity of the problems, the scope of the problems that feel accessible now is just dramatically larger. And also, now that we can write models that I think capture some of what the human mind actually does, I think these models let us generate hypotheses to explain neural data that I've literally had sitting around for 10 years. So this is what I've been most excited about for the last 3 or 4 months. It's actually got kicked off by watching Josh talk about intelligence at the Cognitive Science Society this summer. I felt like what these models can now do, what we can now write with them, let me write down a quantitative hypothesis to connect to data that I literally collected from 2010 to 2015 but could never model. And so I came back super excited and talked some people in my lab into digging up those old data. We've just finally reproduced all of the analyses that we had done back then. And all I could do then with those data is describe them in words. And what feels super exciting right now is to have quantitative models that I think, we haven't done this yet, which is obviously always the most exciting moment in science, is before you've actually done it. So we haven't done it yet, but I feel like if we could have quantitative models of these aspects of the brain system, that we're starting to do that virtuous cycle that Jim illustrated, where models let us, I've had the data, but now if we have hypotheses that could predict those data, we can start to have that virtuous cycle work. In my domain, in my brain area, where Ev says she's been jealous of the vision people, well, I've been jealous of Ev. Like, she's had working models and a brain system for at least 3 or 4 years. And I think maybe now is the time for social intelligence to follow in that same path.
Yeah, that would be amazing. I think, I'd like to think that we're sort of at the early stages of that virtuous cycle. I hope it will work just a little bit. I doubt it will work all the way. I hope it doesn't work zero. But I'm willing to bet that those models will work just a little bit in ways that can then point to the next step. So mostly we'll see the gaps. But then the kind of tools, like Memo as a probabilistic programming language is still very much a growing work. There's other things of how language has to come into the picture. Like the modeling tools are also for this more like higher level cognitive, kind of like the human reasoning. Like that stuff is still just in its early days. Like your guys' study with Andrea, right? You showed really good correlations for like math problem solving, like the things that the models are trained on, but for more intuitive reasoning, it's still quite weak, much weaker correlations, which is, again, that's a sign that we're at the beginning of something good here. So that's very exciting.
And social intelligence lacks good tasks in many ways. I could talk at length on why the social intelligence domain got fixated on bad tasks.
Can you give an example?
Well, the false belief task is a bad task. And for reasons, so in 1978, when testing one chimpanzee, people who are at the beginning of studying theory of mind realized that if you had a creature that could produce a very sparse and purely nonverbal behavioral output, that a good diagnostic test of the sophistication of her reasoning would be whether she could predict what somebody would do when they had a false belief. And so they wrote this landmark paper called The Theory of Mind of the Chimpanzee, and this is Premack in 1978. And so this original paper engendered an entire research program that's now been going for 50 years. And there were many amazing things that came out of it. Again, I can talk for far too long about this, but it led the entire discipline to be fixated on this particular behavior. That is the ability to predict what somebody else will do when they have a false belief. And that was a good diagnostic task. It was a litmus test for a particular, very narrow aspect of social cognition in a particular literal single individual chimpanzee named Sarah. But for actually what we do, when you look at what our social lives are like, false belief action prediction, what will you do if you falsely think that your keys are in your pocket but they're actually in the door, which happens to me all the time. It's nevertheless a very limited aspect of our social cognition. And I'll just say one example of something that I've been finding very important. So in many of the talks that we saw today, the way that the intelligent models become both data efficient and genuinely intelligent is by having world models, right? So that came up in many different talks today. So I think the social domain is a really exciting next frontier for world models because the most important structures in the social domain are invisible. So they're just as structured and just as fundamental to determining what people will and should and can do, but you can't see them. And so here's one example. Whether your relationship with somebody is intimate or hierarchical dramatically changes everything about how you should relate to them, including, for example, how you should address them. So I, for example, frequently tell my children they can address me either as Mummy or as Professor Saxe, but they're not allowed to say anything else, right? So those define two alternative relationship frames that you can have with people. And how you should behave with Mummy is quite different from how you should behave with Professor Saxe. But obviously, I am the same. Every perceptual cue in the situation is the same. All humans know this. So in fact, many languages obligatorily mark in every single way you address a person. If we were speaking French right now, it would be required of every sentence I said to you that I mark whether our relationship is intimate or formal, and also my relative position in the hierarchy. And some languages like Japanese and Thai also mark many other degrees of deference and respect of the topics that we're talking about, as well as the person you're addressing and the audience and context. Language is full of these registers of relationships, in part because they're so fundamental to our social lives. I think they operate like the slopes. So Nancy's amazing task with the slope, where you see the ball falling, and you have to know, is it going to make contact or not? Social structures like relationships are like the slope. They determine the whole sequence of what's going to happen, but they're invisible. And so there's the same problem of world modeling that has the same benefits of efficiency of reasoning, but without the solution that you can see them in the visual input. So that, to me, is the next frontier.
So I agree with that, but I'm going to give a little story that I told Josh a few days ago. So the same Army program I was referencing earlier, we had a workshop because it was intended to be a robot-human collaborative situation. And so there were cognitive psychologists, and there was this very, very good friend of mine named Florian Jensch from UCF. And we're leading this workshop, and we're trying to just set the stage for what it means to have humans and robots working together. And we keep using the word model, and at some point we realized we were using the same word inconsistently. So we said, okay, stop. Let's just actually write down what a model is. So of course, I wrote down a POMDP tuple of states and actions and rewards and observations and transition probabilities and discount factors, et cetera. And Florian looked at it and said, what the heck is that? I said, it's a POMDP. And he's like, well, where is the context? Where's the language? Where's the model of the interactions, et cetera? It's like, oh, good Lord, you can't put any of that in the system. None of our algorithms work at all. You have to, first thing you do, it makes it for non-first order Markov, in which case, what are we even doing here? There are very strong mathematical biases, I think, based on a lot of what makes at least embodied intelligence go for the moment, that is very hard to model what you're capturing. And we should absolutely try. But we are just getting started at this. And
but
so,
I think we might be closer than you think.
You might be closer.
Exactly. Well, let me tell. Let me tell.
I just said first order Markov.
No. Exactly. But no. But as Rebecca said, years ago, the two of us started modeling theory of mind, building these Bayesian inverse planning models related to plan recognition models in AI, and the idea, partly inspired by the false belief thing, although it's very narrow, it is. And you can make it very rich and quantitative and embodied things and have people moving around in environments, but very quantitative.
Not very rich.
Well, a little bit rich. And you can build models. I think some of the joint work we did that I'm most proud of, and that has had, I think, the most impact in AI are these models of social cognition as a kind of inverse planning, where you say, a basic thing that even babies do is see another agent, what are their models of the world, something like their beliefs and desires, and whether it's true, false, graded, and work backwards to figure out the beliefs and desires that explain how somebody has acted, and let you predict how they're going to act in the future, assuming they're approximately rational, boundedly rational, which we formalized as inverting a POMDP. So we stretched those tools and we did what we could. But you're exactly right, and your colleague was exactly right. They only take you so far, and it's not very far. But what we now have, right, the things that inspired Rebecca are a combination of things. There's languages like Memo, which basically let you do much more rich recursive mental state reasoning, and you can also layer on emotional reasoning on top of that, like with appraisals. You can basically use these models to capture at least many of the kind of richer psychological kinds of world models. And by connecting them to language models, like the stuff that Jacob and Andreas talked about, with these ways that natural language can sort of translate into or put distributions over code, if that code is one of these memo models, you can start to get maybe some of the kinds of contextuality and open up your open up your model of people's mental models of the social world to the kinds of things that we talk about in language and that we really only access through language. So I'm not saying we're there. What I'm saying is we're starting to take maybe the ability to have those small steps up the mountain that we couldn't do 15 years ago. And it's exactly, maybe I'll lay my cards on the table, like partly why I'm very happy to have all you guys on this panel is I think, again, the combination of expertise and interests that we have across this group and others in the quest, right, can open these doors, and I think that's really exciting. So,
I wanted, a point was made quickly about context.
Yeah.
And I think that is worth spending a little more time on, because one of the challenges with the way AI is being done in an LLM is it's heavily dependent upon context. But where does the context actually come from? So I think that it's a formulation of the problem. So you're supposed to provide it the context, and if you in your prompt, but if that's an unrealistic way to be interacting with an AI system, and so because you all know that you can't really figure out what the context is supposed to be, and in any case the context is more than you want to put in 10 words or 50 words or 100 words. And so, I think one of the shortcomings of the current architectures is they're based upon a naive notion that somehow you can predict the next word with very limited context. And I'm not exactly sure how you get around that in the current formulation of the problem. So in a way, for an LLM to be useful to you, it would need vast amounts of context on your specific circumstances. And that's actually not represented anywhere. You could give it all your email to look at, but that still wouldn't be correct. And so I struggle with trying to understand fundamentally what's the problem people are trying to solve here. I'm not saying that AI and LLMs can't be very useful in its current form, but we have to be careful to make sure that the problem we're trying to solve actually can be solved with, let's say, the context that we have available.
Am I
right?
Well, this makes me think about something. I'm not sure this is an answer to exactly what you're saying, but it's, I think it might be related, and it's also a story about self-driving cars, only sort of. And it's also an example about how people have thought about the wrong problem in AI. So maybe this is related to the question you're asking. So the problem in AI the problem in social cognition that many AI researchers have thought they should solve, I think is the wrong problem. So this is part of why I was thinking it's related to you, which is they think you should be able to detect from a facial expression alone how the person is feeling. And when they try that, it works generally very badly. And the answer is always, well, that's because what a facial expression conveys depends on the context, right? So they say that, and then they say, well, so therefore we can't solve this problem. But one example of a data set that was used to make that point comes from self-driving cars, where I actually don't know which company this was, thought it might be useful to record the facial expressions of people before they expressed frustration with the self-driving car mode to try to predict when were they feeling frustration. And the answer is that if a person smiles in a self-driving car interface, they're feeling frustration. Because if you feel anything in a self-driving car situation, you're probably feeling frustration. And an expression you often make when you're feeling anything is a smile. And so when they learned what a facial expression predicted reported frustration, it was a smile. And that's obviously an example where if you then learned, well, when people smile, they're feeling frustration, you would have been wrong because of the context. You had to know they were in a self-driving car. So one project that I did in the older kind of inverse planning mode with a student was say, well, for facial expressions alone, just for that problem, what is the context? And the context is your hypotheses about what a person might feel in the situation that they're in. So you have to model their what's called appraisal, so the relevant features of their experience that connect to what they expected, what they wanted, what they feel in control over. So we showed in one small way that a theory of mind model is the right model of the context for emotion attribution. And in fact, which emotion humans attribute to a facial expression depends almost entirely on their expectations of what you should feel in that context, like when in a self-driving car or in a video game show, and very little on the configuration of the face. So it's a perfect example of solving the wrong problem by not thinking about the context.
Let me tell you a related story. So I was on a panel not long ago, and when it was over, someone went up to me and said, why were you so upset with the panel discussion? I thought it went well. And I said, why are you saying that? And they said, well, you were smiling the whole time. And I said, well, the reason I was smiling is before I went up there, someone told me I always look morbid when I'm on panels, and I should smile.
You look great.
This just happened a couple of weeks ago.
Was that panel in the self-driving car?
No, but I don't know. Now I don't even know what to do.
Yeah. So, panels and self-driving cars. Yeah. So, no. I mean, look, these are exactly the points that I think we should be talking about, and I think that again, across all the missions, I mean, we're contemplating a social intelligence mission, and across all the missions, though, I mean, the missions, as I think you can see, the missions were designed to be complementary and synergistic, right? This idea that you saw in all the missions, effectively, that drawing, like, I think Nancy or Leslie had it really well in the EI one, where they're like, here's a thing we've learned: robots, brains, modularity, right? And modular models of the kinds of things that are in the world and how we move through it and how we interact with it. But a really important kind of things are not things at all, but are other agents and minds and their own models of the world and ourselves and so on. And I think, we're moving in that direction, and it's exciting that we're poised to do that. But I would say for the last part of the panel, I think there's a couple of issues that are on, at least I know some of the things you're thinking about for social intelligence, if you're up for talking about them, or I know another thing that Jim mentioned that a lot of us are interested in is, I'm looking more towards impact and things that go beyond individual brains and minds, but where individual brains and minds are at the center of it, but a computational understanding of our intelligence, especially how we think about our social world and our relationships, might be quite important for a number of areas that really matter, and where there's challenges that we're confronting at the societal level. So that includes mental health, and that also includes, call it what?
Education.
Well, education. I was going to say another thing is like civic engagement or something. Like, I think without getting too political, I think it's just an objective fact that in our country right now there are large groups of people who think other large groups are mentally ill, right? And they'll say this. They'll say, like, half the country has a collective delusion, or aren't rational, and you can't talk to them. And it's not just in our country, and it's not just at the national level. So there's something to be understood and some problems to be solved in terms of trying to understand what are, when we look at things like democracies or, faculty committees, we have various mechanisms for trying to scale cooperation beyond the level of like one person coordinating with another to groups, smaller and larger groups. So, I don't know, Rebecca, if you want to talk at all about any of those things, or anybody, like where does our intelligence around world models, especially social models, where does that go for either like mental health, education, or improving society? Anyone?
I can just say just a few words on education.
Yeah.
Nancy and I have spent a lot of time thinking and talking about this recently. It's obviously the case that we learn probably most of what you know about the world, you will learn through language as opposed to direct experiences in the world. And now that we have these models that are really good at producing coherent language, it's becoming harder and harder to probe knowledge, right? Which is a core cycle in education, as you try to convey knowledge in effective ways, but then you also want to make sure.
You mean as teachers, like
yeah,
the kind of thing we do in our jobs. Yeah.
Exactly. And so we've been thinking about in the context of the separation between language and other things, and thinking about what does it mean to understand something, right? Be it coming from the visual input or from the linguistic input. And one kind of idea we're proposing is that for some kind of deep understanding, you really need to take information beyond the visual system proper or beyond the language system. And what that beyond means is probably something like world models of different kinds of aspects of the world, right? So information may come in through language or vision, but then to really get what this structure is and how to connect it to everything else, you have to export it to these higher level cognitive systems. And of course, the field of education is now grappling with this in figuring out how do you test whether somebody really understood
Just put up
some,
your feet. Yeah.
whether somebody actually understood some piece of knowledge they learned through language. And turns out testing through language may not be very effective. And so people are developing these ideas like conceptual maps, which apparently have been around for a while. I just recently learned about them, and other cool new approaches. And maybe there's actually some good synergies that can happen between cognitive science and AI and education, and trying to understand how to probe somebody's knowledge in ways that goes beyond this kind of surface level mimicking of a certain, verbatim string that you've learned.
That's really
I think it goes also to earlier point made, which is ultimately the solution to essentially get more and more data and just scale the thing up. And you might need different kinds of data that we don't have yet. Okay, that would be one approach. Or alternatively, are we missing something? Should the architecture be more modular? Should it have models of physics, models of ethics, models of social interaction, and where you can decompose it and then validate the behavior of the individual models? It does seem that the current architecture is showing shortcomings. So, for example, the whole paradigm, so in a way, safety training is sort of overlaying ethics and social norms onto a model, but that is, to the best of my knowledge, but maybe you know better, pretty ad hoc, and there's no way really to validate. I'll give you, this is just kind of funny. So I just got a robot at home, an industrial arm, and I was using Claude Code to help program it, get it moving around. And so we're writing code together, and then lo and behold, it starts moving the robot without me telling it to do so. And I didn't like that. And so I put in all all caps, do not move the robot, it's dangerous. And then it writes back to me, understood, it is dangerous to move the robot, I won't do that. And so then like 5 minutes later, it starts moving the robot again. And
That's learning like a child.
I mean, right. Right, but it probably wasn't doing it for the reason that you're just. I mean, again, as we know from humans, it's one thing to be able to say, okay, I won't do X, but that's not the same as understanding that you shouldn't do X, or actually being somebody who can hold to a legitimate commitment.
It's not a constraint.
Not to do X.
It's like everything is a suggestion.
Yeah.
Give it a few years.
And again, I'm glad you mentioned sort of moral or ethical sense, because again, this is something that a number of us have worked on. That some of Rebecca's early work studying the brain regions involved in theory of mind, the famous RTPJ. Those brain regions are essentially in a necessary way, not just correlated, but they are causally involved in making inferences about somebody's moral status. The famous Grace studies, did somebody do something by accident that happened to kill someone, or did someone intentionally try to kill someone and it didn't work? The difference between attempted murder and so on it's about intent. And these parts of the brain are selectively involved. You can see this in fMRI, but you can also use a brain zapper. You can intervene on the brain and temporarily deactivate those parts of the brain and then change somebody's moral sense. And they start, instead of thinking about intent, just think about outcome. So again, I think that comes back to also something that I know Jim is interested in, is if we really understand the brain, whether it's at that kind of macro level or at a finer grained computation and neural circuit level, we should be able to intervene on it to have positive outcomes, not to turn people temporarily into sociopaths, but or whatever economists, but just to but to try to help. So I don't know. I mean, or I don't know if Jim wants to comment, or if anyone thinks like, is that an area that we in the Quest should be thinking about? How can we use our understanding to actually improve mental health, whether it's through mechanistic neural implementations or interventions or behavioral therapies? There's a, to put up another North Star kind of goal, and again, I know I'm not the first person to say this, but a thing that a number of people have said over the years is, imagine if psychiatry were like cardiology, right? I mean, cardiology is one of the great success stories of modern medicine over the last 5 or 6 decades. I mean, it's amazing how much, right, I mean, the biologists know this, right? A principled understanding of the heart as an organ and the organ system that it's at the heart of, what its function is and what are the mechanisms by which it achieves it, has enabled medicine to make huge strides in improving cardiac health, because you can not only diagnose but predict the ways that it will break, and you have so many kinds of interventions, whether it's surgical or pharmaceutical or electrical or behavioral. It's amazing, okay? And imagine if our understanding of the brain and the mind were like that. There's a field of computational psychiatry, is sometimes called, which has been around for almost 2 decades and is starting to gain steam, but it's still pretty at the very earliest steps up the mountain, and it really has focused a lot on reinforcement learning and decision making, not the whole space of world models and social and language things here. So I don't know. I see that as an area where we really could have huge impact in ways that connect the basic research to things that matter.
And a really important complement to all the beautiful mouse work that's being done, because it's just really hard to study schizophrenia in mice or autism in mice.
Yes.
It's a very, very limited kind of model.
Yeah, or social anxiety disorder, or I mean, there are analogs of that, but
for sure.
It's amazing how much so many ways that humans have found to be smart have all these flip sides of all the ways we make problems for ourselves and the people that matter to us. Anyone else want to talk about other areas of impact?
I wanted to add to that is to flip it around also. Robotics is continuing to evolve. Robots are starting to perform more and more sophisticated tasks. There's a future where, so right now, most robots, with very few exceptions, I guess self-driving cars being the best one, and maybe vacuum robots, most robots are very carefully segregated from humans. For not the least of which is you can't always predict their motion, but for a variety of reasons. But as robots get more and more capable, we are either going to lose more and more of our work sort of existence, or we're going to have to find a way for robots and humans to coincide. And it's not just about safety, but actually being able to work together. And so I think like all of the issues that you're describing related to like possible human mental illness, but also like even for humans that don't have specific mental illnesses, you still want the robots to understand and have that theory of mind in order to be effective teammates, so that like the nature of our work is going to change, but we kind of want the nature of our work to change positively when engaging with robots, and that's not something I think we know how to do right now. There was a very I was watching the football game last night, and there was a very surprising ad for Meta. And Meta was, it was a little narrative of this fellow who worked in, out in the field, like it wasn't like somebody working in an office job. And what he observed is like he was never home for dinner. And then Meta started building this data center, and now all of a sudden his work had changed. He was working in the data center, and he got to be home for dinner. First of all, I thought, what a surprising ad for Meta to put in a football game. But then also it's just like, okay, if that's how work is going to change, is that a short-term job? Is that a long-term job? How do we actually like build an intelligence that's like actually going to like help that specific person in this particular ad, but also many more people actually continue to have jobs, long-term? And it's almost certainly going to involve working with artificial intelligence in very concrete ways. And that artificial intelligence better know how to work with humans too.
Yeah.
Surprising
right. I
ad for
think that's,
football
again,
game.
it's the thing that motivates many of us is increasingly, the world that humans live in is a world that AI is inhabiting and reshaping. The AI in turn is coming into a human world, a world that we built for ourselves, for better or worse. And it's one way or another, we have a shared future. So the more that we can that we can understand in the same kinds of engineering terms that we use to build robots, the more that we can understand our own minds, and especially how our minds understand or misunderstand each other, then the more we can build robots and other kinds of agentic AI systems that will be forces for good and thriving.
It's very telling that with self-driving car implementations, they're not end-to-end AI at all. And the implementation still use good old stuff like finite state machines and if-then statements.
Poppy peas.
And why do they do that? They're doing that because you want to make sure you don't have unpredictable behavior, and so no one trusts even at the biggest projects that have been going on for a long time. No one trusts the machine learned stuff to handle the critical functions, and so that is like a big question mark. How do you get over that barrier? And a self-driving car is a robot. It's actually a very simple one. It's in 2 dimensions, and it's working in a constrained environment. Like if you take this to the next level, and you're like looking at humanoid robots or things operating in much more unstructured environments, it's really looks to me like a very hard problem.
Yeah, we're pretty much. Who says that? Yeah, we're pretty much at the time. Does anyone from the audience want to have any questions? Yeah, go ahead. Or comments.
I know everybody knows, but I just feel it needs to be said.
Yeah, please.
In order to function in a society with increasing amounts of AI,
Yeah.
it will be important not only for AI and humans to understand each other, but for humans to think very hard about how they're going to treat other humans. And the fact that they're going to take care of other humans who are going to be put out of work and otherwise impacted by AI.
Absolutely. Anyone else have thoughts, comments, questions, injunctions, warnings?
Benedictions?
Yeah, Barry?
I just think Rebecca Saxe's work is it's really critical for where we are today. And so I'm just delighted to come and to have learned that this is a step that you're taking. Because it was so interesting to learn the difference between language and thought, and yet we're sort of using words in both of them. And I think what's happening today is people are thinking that they're talking to each other, but what they really want to express more is how they're feeling, and so we think the words we're using are having a conversation, but of course they're clearly not. And I'm stuck here, so I'm going to just say, because I can't find the words to talk about this, thank you for doing it, and look forward to it, but I see how it melds with what the rest of you are doing.
Yeah.
So this is just critical. Thank you very much.
That's so great. Thank you. It's we're used to seeing, like in mathematical reasoning, this is one of the latest areas where language models are trained to solve math problems. And originally it was, just addition and subtraction and multiplication. And then it was math competitions, and now it's the International Math Olympiad. And some of the world's smartest mathematicians are trying to work with AI systems to, prove new theorems and advance the frontier of mathematical knowledge by proving theorems. But fundamentally, the part of why AI works on that is it's yet another game. With a well-posed solution, right? Like if you have a math problem, you've either solved it or you haven't. If you have a theorem, you either proved it or you haven't. Just like if you're playing chess, one person wins or not, or it's a draw, or in Go, and so on. And AI is very good, and reinforcement learning and machine learning is very good at playing games. And there's rules, some of those games are really important. Like being able to solve math problems is really important in a lot of areas in advancing humanity in good ways. And there's some people who are really, really good at it, and a lot of people who are less good at it or have spent less energy or whatever it is. We could say maybe the same is true for emotional intelligence, right? Some people are amazing at it. Other people, maybe they could use some help. But just as mathematical reasoning is one of these areas where it's really important, and there's a wide range of capacities and interests, and in that, same with emotional intelligence. But it is quite possible that you can understand emotional intelligence as a computational process with mechanisms and algorithms and architectures that are built into the brain and that also develop, and language helps. And it's not the same kind of well-posed logical problem that math reasoning is, but it is a computational problem, potentially. At least that's part of the thesis here, and the kind of work that Rebecca has done. So if we could understand emotional intelligence in computational terms, including the spectrum, the range of individual variation, and maybe build tools that might, that could offer positive value and might even help some people think about the kind of things that Nancy was talking about too. Yeah.
Let me just ask you, because is this a scaling problem, or is it a magisterial problem? And that kind of has been in my mind throughout this afternoon's conversation. And if it's just a scaling problem, just get a bigger computer, right?
It's, well, fundamentally, the reason we're here is it's not just a scaling problem, right?
But so, and my guess is we have not described the magisteria in ways.
I love you using that word because Nancy uses that word too, right? No, it's great. Like, okay, probably, yeah.
But
Well,
problems that have been solved are delimited. And what we run into trouble when we believe a problem is delimited, and guess what? It's not. So.
yeah, I mean, I would say, in Silicon Valley, they like to blur the boundaries between these magisteria, I think, and to say, let's make it all a scaling problem. But if you look at the brain, and this is Nancy said exactly this, those are different magisteria in the brain. and so neuroscience and cognitive science can help us, give us a perspective there, but also the computational tools that these folks are developing can actually start to characterize these different magisteria and say, well, like, again, I think it would be a mistake, this is a bet, but we'll see, to say that emotions aren't computational. They won't be the same kinds of logical calculations as math, okay? But they could be computational in the sense of the kind of models that we're trying to build and learning how to build here. So this is just open. I think we might expand what we mean by computation. Many people see computation as inherently opposed to something like emotions, but if you look, right. Anyway, I think that this is just, we're going to have to see where this goes. But this is a place where the kind of bets that the Quest is making very different from the ones that the tech industry is in a position to make. And I think, as we go up our sides of the mountain, we'll have to see what that looks like. But I think it's going to be a really important area for the work here and its interface with the broader world.
A quick comment about scaling problems. So in computer science, many algorithms can be trivially solved by scaling up the data. It's always been the case. I mean, you could sort numbers by having every combination of random numbers and the sort or exhaustive search. It's all about the combinatorial complexity, and so no one knows today on for example transformer-based LLMs, what the kind of equivalent of scale-up computational complexity would be for different problems. So yes, it could very well be that almost everything we're trying to do could be solved with sort of an infinite number of computational elements over an infinite amount of time. The real question comes down to, in many cases, how do you make the problem tractable? And I think Josh or someone here made that comment earlier today. And so I suspect that the current set of solutions that are out there aren't going to scale up because you're going to hit complexity limits in a way.
Any last comments from our panelists?
I think we should give David the last word.
Okay. Thank you, panelists. Thank you, David. Thank you.